Hi, so continue from last video about acids and bases. We looked at two different theories. So one is your Arrhenius' theory about your acids having that H plus. So if we were to scroll back up here, this is Arrhenius' theory about your proton that gets associated, that makes it an acid, which we see a lot. In bases, it's the hydroxide ion that gets associated, which we see a lot in our bases. But a problem that we run into is ammonia, because ammonia is a base and it doesn't dissociate this OH hydroxide ion. So how do we sort of come together with this one? That's where Bronson and Lowry, that's what we talked about, how acids is not just your dissociation of your H plus, your proton, but it's actually the donation of your H plus to the other base pair. And then a base is the accepting of this H plus. So we no longer talk about hydroxides, it's more of the movement of your hydrogen ion. So then we looked at the different base pairs and now we can actually look at the general form of this. So last video we left off right here. Let me just kind of get my pen. So ammonia is right here as a base. How do we classify this? So right here, this is ammonia is the base because remember, a base is your proton acceptor. So that means that it's going to take in a proton. Where is that proton from? Well, you have to look at the pairing of this. So where is this paired into? Remember, this is all in solution. That means that there's water that's part of it. So then water is actually going to donate your proton, your H plus, which makes your NH3 to be an NH4, and because your water has lost this proton, now it's no longer H2O but hydroxide ion. So then there's actually a couple terminologies here, and we know that your NH3, your ammonia, is classified as a base because it has accepted this proton. But then when we look at this acid and base, there's always a pairing. That means that if you have a base, something must be an acid. So where did this proton come from for the ammonia? It came from your water, and because your H2O was your proton donor, it donated H plus. So according to Bronson and Lowry, this one must be your acid. So then if we were to look at the product side after this has happened, well then ammonia actually has this extra positive proton, and then your water becomes a hydroxide, which is your base. And we can talk about the base pair here is that now this is where you have your base pair, that because ammonia started off as a base, now in the product side your ammonia became ammonium with this charge. This actually is your conjugate acid. So that means that in your product side this acts as your acid because now this has the extra proton to donate back to your hydroxide if this solution were to go back the other way. Okay, so the base pair here is that ammonia is your base, and then the conjugate, and it becomes a conjugate acid. So this is your acid base pair, and then water was your acid, and then in the product side it has lost an acid. So this one now can accept your proton. So this is actually your what they call the conjugate base. So on the product side it acts as the base. So then the conjugate acid base pair is that you have to look at this. Your water started off with your H2O. It donated your H plus. That means that now in the product side it is a OH. In the product side now it acts as a base. So this is what they call the conjugate acid base pair. It was acid in the beginning, now it acts as a conjugate base as a product. Likewise for ammonia, in the beginning it accepts a positive proton, so it is a base, but now in the product side it has an extra proton. Now that's your conjugate acid. So this is your conjugate acid base pair. So there is actually a general form for this. So looking at this one, this HA, this H represents your H plus. This A represents your acid. So this is the general form of your acid. And then for the base, that means that this is going to accept your proton. So that means that this H is going to be donated to your water. So if you look at the product side, this A now would lose, this acid will lose your proton, so that makes it a negative charge. That's why it is a negative ion. Whereas the water here, it accepted this H plus. Remember, this is the H plus from the acid. Now it will become this H3 plus. So how do we classify this conjugate base pair? That's really what we're talking about. So acid, you donated it, so that means that in the product side this becomes your base. That's your conjugate base. So you have your acid to your conjugate base, and then your base accepted a proton. On your product side, it becomes your conjugate acid. That means now in the product side, this acid can accept protons or donate protons. So that's your how you define these ones. Let me see what we have in the next one. Okay, so this is your base form. So base starts off with your B, and then because base has to accept your proton, so then this water is going to donate, right, your hydrogen proton. So this becomes your BH positive. Remember, this is just a general form. The B represents your base. Now it has gained that extra proton to make it sort of the conjugate acid, right? Whereas your acid, you donated your proton. So then in your product side, you have a base. This will become your conjugate base. So all this is just looking at the base pairs and the conjugate acid and base. That means that it's what happens after in the product side. So if you have an acid to begin with, it would become a conjugate base as a product. If you start it off as a base, it will become a conjugate acid after it has reacted. So how do we apply this knowledge? So here's the first question. You have HSO4 negative reacting with CO3 2 negative. So which one is going to be your acid and which one is your base? So to define or to look at this, to answer that question, then we have to look at what happens after this. So let's look at HSO4. It started off with an H plus, and then it ended up without the H plus. That means that that H has to be donated. So we had to move this proton to your CO3 2 minus. So this has to be your acid, and if this is the acid, this is the base. Is this right? Did this accept a proton? Yeah, it did, because if we were to look at the product, this is your, it has that extra H here, and your SO4 has lost the H. So then which one is my conjugate acid and which one is conjugate base? All you really have to do is find the same chemical sort of the compound, SO4, that's your sort of your backbone of your compound here, and this is your CO3. So then if this is your conjugate acid, and this is going to be, if this is your acid, this is going to be your conjugate base. And then this was your base, this must be your conjugate acid. So does that make sense? Will this HCO3, are they able to donate to the other one? Yes. So if that is the case, then we got this right. So this is acid and conjugate base. Let's look at the next one if you want to just kind of stop the video and try it on your own. So this is another one right here. So we have your HCO3 minus, your hydroxide, carbonate, and then water. Let me move this out of the way. So then again, we have to determine which one actually donated proton, which one didn't. So let's look at the CO3. Starting with the H, and then now you lost an H. That means that this had to donate your proton to the hydroxide ion. So this one has to be your acid. Did your hydroxide accept a proton according to Bronson and Lowry? Yeah, so this accepted your the proton from the other one. All right, so let's look at your product side and see which one's your conjugate acid and which one's your conjugate base. Well, if this one is, the CO3 is your acid, let's connect this with your CO3. This one must be your conjugate base. And then if OH, we're going to find the sort of the same skeleton to water, and this one must be your conjugate acid. So we can even look at the product side. Can this water donate a H plus back here to go back to its original state? Yeah, it can, because it has the extra H, and this one has one less proton, so it can accept a proton, and that becomes your conjugate base, because it will become your proton acceptor in your product side. So that's really what conjugate acid base pair is that in an acid and base, you always will have an acid. If you have an acid, there will always be a base. And once it reacts, then you can determine which one's your conjugate acid or base based on its proton accepting or donating behavior. So that's really your Bronson and Lowry. Hopefully this video has helped you identifying your conjugate base, conjugate acid in the Bronson-Lowry base pair. So thanks for watching.